Hi everybody. So in this video we're going to introduce how we classify minerals, and we're going to start with the silicates. The silicate minerals are a group of minerals that are based on a so-called silicate tetrahedrons. They start with a silicon atom in the center, and there are 4 bonds that emanate outwards from the silica, and those atoms are bonded to oxygen. Oxygen here in blue, another one, and then 4. So the reason for this kind of pattern has to do with the relative ratios of the radius of the silicon atom and the radius of the oxygen. The way they can pack together is in this kind of arrangement where we have a chemical unit of SiO4. Now, the atoms themselves are not the same size. The silicon atom is very small, and the oxygen atoms are very, very large. The oxygen atoms they're packing really dominates the structure, dominates the shape. And so what we could do is we could draw a line that connects those oxygen atoms. And what we get, if we just draw the same pattern off to the side here, but ignoring the drawings of the atoms themselves, is we get this little 4-sided figure that we refer to as the silica tetrahedron. So tetrahedron. Tetra is the Greek root for 4. So this is just saying that we have a 4-sided figure. And so that just has a lot to do with the geometry of the way silicon and oxygen pack together. Now, if silicon atoms all have a 4+ charge, and the oxygen atoms have a 2- charge, and they do, so oxygen with a 2- charge, then we have a +4 over here, and then a -8 with 4 oxygen atoms being bonded to it on the negative side of the ledger. And so adding all those together, we get a structure that has a total charge of 4-. So this is not neutral. This thing has a charge. So it's structurally stable because of its packing, but it's not electronically stable. And so silicate minerals are minerals where these tetrahedra, these guys here, the silicate tetrahedra, are the basic building block, and then they're bonded to one another. We could have them bonded directly to one another, where we have a tetrahedron, and let's say it shares a corner with another tetrahedron, and this could go on infinitely. Or we can have a different situation where we've got a tetrahedron over here and another over here that's not directly connected to that first one that I drew. But it could be that they're connected by another atom that served as an intermediary that bonds these two things together. So for example, we can have magnesium, which has a 2+ charge. If we have 2 of those could bond with the SiO4 units that have a 4- charge, and those two magnesiums would satisfy charge balance, and we'd have Mg2SiO4, and that's a member of the olivine group, and it's a mineral called forsterite. So the bottom line is that all of the minerals that have these SiO4 units are part of a group called the silicates. So there are other minerals that are chemically analogous, not really similar. They're going to have very different properties, but we can also have phosphorus at the center of one of those tetrahedra, and we'd have PO4 units. And phosphorus also commonly has a 4+ charge, and so we would have PO4 unit with a 4- charge. It's supposed to be a 4-, so let's rewrite that. So those building blocks would be the basis of a group of minerals called the phosphates. And then we could instead have sulfur as the central atom, And those building blocks would be the basis of the mineral group called the sulfates. We could have tungsten in the center of one of these tetrahedra. And so that would give us the tungstates. You could also have molybdenum, and then you have a group called the molybdates. So there are these chemical groups, these things called the phosphates, sulfates, tungstates, etc. They're all dependent on these anionic complexes which form the fundamental building blocks. So those are going to be groups of minerals that if you're enrolled in a mineralogy class, you'll see in your laboratory part of the course. Now, there are fellows that are a little bit more chemically simple than that. There are, instead of the sulfates, there are the sulfides. So if you look at all the groups that we just looked at, you look at their formulas, oxygen is the dominant atom. And that is not surprising in that oxygen is the most dominant atom in all of Earth. It's the most abundant element in the crust. It's the most abundant element in the mantle. The only place it's really absent is in the Earth's core, where iron is dominant, not as an oxide, but as a metal. But there are other anions that can form the basis of mineralogical structures. And if it's sulfur, then you can have sulfides. So you can have something like mercury sulfide, which is the mineral cinnabar, or you can have arsenic sulfide, which gives us realgar, or you can have something like iron sulfide. Let's say Fe(S2), and that would be a mineral such as pyrite or mineral marcasite, depending on how those iron and sulfur atoms are structured. There are also mineral groups where chlorine is the dominant anion, and so we would have the halides. So here is sodium chloride for halite, or potassium chloride, which is the mineral sylvite. So instead of oxygen, now here chlorine would be the dominant anion in these groups. We can also have minerals where instead of oxygen being the dominant fellow, it would be a combination of oxygen plus hydrogen. So oxygen is a 2- charge, add hydrogen with a 1+ charge, and you get a hydroxide, or the OH molecule. If we charge balance that with something like magnesium, magnesium is a 2+ charge, so we could take 2 of those hydroxides and add them to magnesium, and we get something like brucite. And so this group of minerals are the hydroxides. And then coming back to the oxygen-dominated fellows again, there's a very important group that we left out in the earlier part. We can have a central atom that is 4+, but if that atom happens to be carbon, carbon is so small that only 3 oxygens can fit around it instead of 4. And so instead of PO4 or SiO4, we don't get CO4, we get CO3. We get the carbonate unit. And in this carbonate unit, carbon still is a 4+ charge like those other atoms that we saw, but we have only 3 oxygens, so that's a total charge of -6, so -6 and a +4 gives us a 2- charge on this. And we can combine that with something like calcium. So a calcium plus carbonate unit would give us CaCO3, or the mineral calcite. And that didn't come out very well, so we'll try redrawing that. So the mineral name here is calcite. And then as a final group of minerals, we have the so-called native elements. And for the native elements, we often have things that are metallically bonded to one another. So we can have copper or silver or gold. And if these are metallically bonded to one another and no other anions are playing a role, then we just have the pure metals. And those would be part of the native elements. The other kind of native elements that we can have are non-metallic. So these are native elements that are metallic. And then we can have copper, which is the basis of graphite or diamond. If you're lucky enough to find one of those. So in this case, this is a non-metallic.